Okay, I want to talk a little bit about significant figures and where we get significant figures. Significant figures arise because there is uncertainty in measurement. Okay, uncertainty in measurement. For example, I have a top loading balance here, and you can see that it measures out to 2 decimal places, and I'm going to put this rubber stopper on the balance, determine its mass. So we have 38.53 grams. So the question I asked, does that mean it's 38.53000000 grams? No, of course not. We don't know what goes out to the right past the 3 and the 4. You see the 3 and the 4 oscillating back and forth. We don't know the values out there, but values do exist out there. But this balance cannot pick up on them. The sensitivity is not great enough. Now you see that this 4 and 3 kind of shift back and forth. This analytical balance, by design, is sensitive to the hundredths place. Right? By definition, the uncertainty, the first digit that is uncertain, is in that place, right? Where that 3 is right now. And so when we record a mass measurement or any kind of measurement, we record where the digit, where the uncertainty first arises, the digit where the uncertainty first arises. So if you determine this mass on this balance and you're writing it in your notebook, you would take all these numbers. 38.54. Okay? Maybe it's 38.53. Maybe it's 38.55. But it's going to be around there. But the point is, in the hundredths place, that digit is uncertain. So we take 4 significant figures in this measurement. Now let's go over to a more sensitive balance. This is an analytical balance. Put the rubber stopper on the balance. And now this balance can pick out on those numbers that are out over there. 38.5428. Similarly, this balance, by design, the uncertainty first arises out at the 4th decimal place. The 4th decimal place. That's where the uncertainty is. So if we're recording a mass measurement using this balance, we would have 6 significant figures. 6 significant figures. We don't know what's out to the right past the 8. This balance can't pick it up. There are values out there, and it's very unlikely they're all going to be zeros. Okay? So we can't record 38.5428000. We just don't know what's out there. That, in essence, is where we get our significant figures. This has 6 significant figures. This measurement has 6 significant figures. This measurement has 4 significant figures. Okay, now there are 2 types of measuring instruments that you would use in the lab, that you would use in general chemistry. One is digital, right? Digital balances, digital thermometers, and like we used over here on this top loading balance and on the analytical balance. And it's easy to get the number of significant figures on these because all you do is just record all the digits you see. Graduated instruments, a little bit more complicated, not too much though. And to illustrate this, I'm going to use a ruler. So, don't know if you can see, I have a line here that we're going to measure using this ruler. What you see up here on the top are centimeters, all right? So this is 1 centimeter, 2 centimeter, 3 centimeter. The smallest divisions up here are in the 1/10 of a centimeter, so those are millimeters. Millimeters. So, try and put this ruler up here to measure this line. And I get something like that, right? So, yeah, it's really difficult using this phone. Okay, let's leave it right, no. Just a second. Okay, let me see this. So now I'm measuring this line. And you see here, it is, well, it's at least 2 centimeters for sure. And then we have 2.1 centimeters, 2.2 centimeters, and it doesn't quite reach the 2.3 centimeters. All right, doesn't quite reach. So we have to estimate in between the 2.2 and 2.3 centimeters. Right, we're estimating there. And so I look at this and it looks like to me it's probably going to be about 2.3 2.28 centimeters. 2.28 centimeters. Okay? I'm estimating. Maybe it's 2.7. Maybe it's 2.27. Maybe it's 2.29. I'm estimating in between there. Right? So that's the digit where I'm uncertain. I'm going to record that as 2.28. 2.28. In doing so, I get 3 significant figures. Again, the level of uncertainty determines my significant figures. Now, a rule of thumb on graduating devices like this, the smallest divisions are in the 10th place, right? A tenth of a centimeter is the smallest division. The uncertainty then, the last digit we record in our measurements, where we estimate, is 10 times smaller than that. It's a rule of thumb, right? General rule of thumb. So if the 10th place is the smallest division, in this case, the 10th of a centimeter, then the estimate has to be in the 100th place. And the 100th place is the last digit that you record. In this case, it would be 2.28, and 2.28 gives me 3 significant figures.
Okay, now that we've discussed significant figures in measurement, basically where significant figures come from and how to record significant figures from an analytical balance and a graduated instrument, we need to be able to read significant figures. Read significant figures. There'll be times you'll be reading a notebook or some other scientific work and someone has recorded significant figures. They've made a measurement and they've recorded significant figures. And you need to be able to read the number of significant figures in their measurement. And it's pretty straightforward. A lot of times I think we throw too many rules out there and it tends to confuse students. But I just want to point out it's all about the zeros, right? Zeros are what are confusing. Zeros, sometimes they're significant and sometimes they're not. But it's important to remember that all non-zero numbers are significant. That's pretty easy. So we're only left with the zeros. Is a zero, particular zero in a measurement, is it significant or not? That's what we have to determine. Couple rules, well, 4 rules I put up here. I've already mentioned the first one. All non-zero numbers are significant. All zeros between 2 non-zero numbers are significant. All leading zeros are not significant. And all trailing zeros are not significant unless there's a decimal point. I'll get into what we mean by leading and trailing here in a second. So let's assume that we have some numbers down here. These are measurements that somebody has recorded. And we're assuming that they've recorded them correctly and they are intending the correct precision for the recording. In other words, they didn't make any mistakes in their recording of their measurements. And these are measurements of some sort. I didn't put any units out here just to make it as universal as possible. So this could be grams, this could be centimeters, it could be kilometers, whatever. So this first number up here, that's pretty easy. How many significant figures are in this value? Well, they're all non-zero numbers. Therefore, they're all significant. So we have 5 sig figs here. 5 sig figs. What about the number 401? 401. Well, by the second rule, all zeros between 2 non-zero numbers are significant. So this 0, it's between 2 non-zero numbers. So that 0 must be significant. There are 3 significant figures in this value. What about the next one? All leading zeros are not significant. Well, this is what we mean by leading zeros. We read typically from left to right. So these are considered leading zeros. Both of these zeros are leading zeros. In all cases, there are no exceptions to this rule. All leading zeros are not significant. So in this value, we only have 3 significant figures. What about the next one? We have 2 leading zeros. They're not significant. We have a 0 that is in between 2 non-zero numbers, so that 0 is significant. And we have a trailing 0. Interesting. Now all trailing zeros up here, all trailing zeros are not significant unless there's a decimal point. Well, we have a decimal point. It's right there. So that's trailing 0, but since there's a decimal point, that 0 is significant. 4 significant figures. All right, and the last one. This 0 is in between two non-zero numbers, so that 0 is significant. This is a trailing 0, and there's no decimal point, so that trailing 0 is not significant. There are only 3 significant figures in this number. Okay. Now, why is all this important? Well, because we typically use significant figures in calculations. And I want to point out something. So let's say that I'm going to multiply 2 measurements together. Say we have to do it for some reason. Our lab report. So 3.21, and I'm going to multiply it by 4.27. 4.27. And we're assuming these are measurements, right? So there's precision involved here. There's a limitation into our measurement. We know that this value is uncertain because that's the last digit we recorded. That's why there are only 3 sig figs. And this digit is uncertain, right? We're not sure that's a 7. It's around a 7, but we're uncertain. We certainly don't know any of the values out to the right, or any of the values out to the 1 here. So I'll go ahead and put that in my calculator. 3.21 times 4.27. And what I get is 13, and you probably should do this at home, 7067. Okay. Now, not all these numbers that I've written here in this calculation are valid. They're not valid. What do you mean they're not valid? We use a calculator. That's what the calculator gave us. Well, they're not valid because when the calculator does this calculation, it assumes that this number is 3.2100000000 out to like 9 decimal places. And this value is 4.27000000 out to 9 decimal places. You can actually try that at home. You can plug in 3.2100, give it as many zeros as your calculator will take, and multiply it by 4.27, give it as many zeros as your calculator could take, and this is the number that it will come up with. But remember, these are measurements. We don't know that there are zeros out here. We don't know if there are zeros out to the right of 1, and we don't know if there are zeros out to the right of 7. It's unknown to us. We can't measure that far. Hence, some of these values out here are nonsense. Right? This is only true if there are a bunch of zeros out here. A bunch of zeros out here. A bunch of zeros to the right of this 1, a bunch of zeros to the right of this 7. That's where this value is only valid. But we don't know that there are a bunch of zeros out there. We can only record in our calculation the values that we're sure of. And the rule is, in multiplication and division, this applies. Right? The number that's involved in your product, the number that's involved in your mathematical operation and multiplication, whatever number has the fewest significant figures limits your answer to the same number of significant figures. So we have 3 here and 3 here. That means we can only have 3 sig figs over here. So these are crossed out, and we can only record 13.7. 13.7. That's the only thing that we're sure of based on our measurement. What happens if it's 3.2 multiplied by 4.27? My calculator gives me 13.664. But we only have 2 significant figures in this number. 2. We have 3 over here, but only 2 here. So this value can only have 2 significant figures. Right. We're only sure of two values here. So these are dropped off, and this is rounded to 14. And to 14, the 6 is greater than 4, and so 3 is rounded up to 14. Okay? Two significant figures limits our answer to two significant figures. That's the rule in addition, in multiplication and division. That's the general rule. Addition and subtraction is a bit different. So think back, and I don't know if they still do this or not, in elementary school, think back when you're putting numbers in a column and adding them together. Let's add these two numbers. Instead of multiplying, we're going to add these together. 3.21 plus 4.27. Add them together. 7.48. Okay. Let's add these two together. 3.2, 4.27. Okay. Now over here, we use the rule that we learned in elementary school. We have to assume that this spot right here is 0. And again, this is a measurement. We don't know if that's a 0 out there or not. We have no idea. And so this entire column becomes unknown to us. Unknown. We have no idea what that value is out there. Remember, this is where the uncertainty first arises, in this column, right, in the tens place. So the tens place is the last digit we can record in our calculation. So this value, this calculation, addition, can only result in 7.5. Right, we round the 4 up to 5, and that becomes 7.5. This is nonsense. We don't know. We don't know what we're adding the 7 to. Have no clue what it is. We're uncertain about this one, remember, because it was the last digit recorded from our measurement. And this applies for addition and subtraction. It's basically the column, the decimal place, where your uncertainty first arises. That limits the number of significant figures in your answer. Now you can gain and lose significant figures in addition and multiplication. For example, let's say we have a 5.2 and we have a 7.13, and we're going to add these two numbers together. Adding these together. Through also addition here. So, using the rules that we learned in elementary school, this becomes a 3 over here, that becomes a 3, and this becomes a 12. 12.33. Where does the uncertainty first show up? Well, it's in this column right here. That's the digit we last recorded in this measurement. So that makes this entire column the first place where the uncertainty first arises. This is nonsense over here because we don't know what we're adding 3 to at all. Have no clue what it is. So this is gone. So we record this as 12.3. Now note, it's a bit different than the the multiplication and division up here. Multiplication and division, we had 3 significant figures in both these numbers. That limited our answer to 3. We only had 2 significant figures here, 3 over there. This limited our answer to 2 significant figures. Down here, a bit different. We have 2 significant figures in this answer, this value. 3 significant figures here. And our answer has 3. Okay? So this number doesn't limit the number of significant figures in our answer the same way it does in multiplication and division. Again, when you're adding and subtracting, it's all based on where the uncertainty first shows up, right? What column, what decimal place does the uncertainty first arise? And in this case, it first arises in the tenths place, in this number. Therefore, our answer can only be recorded to the tenths place. So that's some of the reasons why we keep track of significant figures in our calculation. Let's say that we have some calculations where we have both addition and subtraction and multiplication and division in the calculation. So let's say that we have 7.1 plus 3.2, and this is going to be divided by, I don't know, let's say it's 5.0. Well, I'll call it 5.01. 5.01. How many significant figures are going to be in our answer? I'll tell you. It's going to be 2.06. 2.06. We can only have 3 significant figures in our answer here. If we add these together, these two numbers together, we get a value of 10.3. And the tenths place is where the uncertainty first arises, so we stop at the tenths place. And so we get 3 sig figs up here, and we have 3 sig figs down below. So now we do our division, and we end up with 3 significant figures for our answer.